Globally, only 3% of our energy is currently produced by renewable technologies, or 13% if you include biomass and waste. The predominant fuel sources are currently oil, coal and gas. In 2006, average world energy use per capita was 72 million British thermal units. However, this energy is used at a disproportionately high rate by developed countries. In the UK, the average per capita energy use was 162 million British thermal units in 2006, 10% higher than the European average. It's far too easy to compare ourselves with the likes of America and focus on what we think they should be doing, but we need to remember that we, in the UK, each consume more than double the world average per capita, and just to put that in context, that's over 10 times the amount consumed by the average African.
In the UK, the energy used in constructing, occupying and operating our buildings accounts for 50% of our greenhouse gas emissions. Of this energy use, 90% takes place in the in-use part of a building's lifetime. If all energy used in buildings for heating, lighting, hot water and equipment was met by low-carbon technologies, this would reduce total UK carbon emissions by over 45%.
In 2007, Scotland generated 48,000 gigawatt hours of electricity and consumed 40,000. 17% of this electricity was generated from renewables, and as we've seen, this proportion is planned to increase. The emissions from any one particular energy source can be calculated with a reasonable degree of accuracy through a thorough life cycle analysis, as we'll see later. Producing 1 kilowatt hour of electricity from coal emits 40 times as much carbon dioxide as producing 1 kilowatt hour from renewables. Looking at where Scotland's electricity comes from, we can apply conversion factors to the totals from each fuel source to show the true impact of current electricity production. Currently, the average emissions per kilowatt hour of Scottish electricity are 0.446 kilograms of CO2. There's huge scope to reduce this dramatically to an almost negligible level, as it's estimated that there are over 60 gigawatts of available renewable resources in Scotland, equivalent to 10 times current demand. Let's have a quick look at some of the solutions. Renewable technologies are able to generate electricity and heat with zero emissions, apart from those resulting in the energy embodied in the technology itself. The UK currently has just under 2,000 megawatts of renewable electricity generation installed. This falls far short of the potential capacity of 75,000 megawatts. Only 0.6% of total UK heat demand is met by renewable generation. The UK has fantastic potential for heat and electricity production from hydroelectricity, wind power, wave power, solar energy and biomass, with annual potential for solar electricity generation alone able to meet 2/3 of electricity demand. There's many options for producing heat and electricity from renewable sources. To address the emissions that we create by keeping our buildings warm, heat can be produced by burning biomass, fuel made from organisms that were recently living. It can be used within individual homes, in stoves or in a community. Burning biomass is carbon neutral, as the carbon dioxide is absorbed during the life of the organism. It's also extremely cost effective and is cheaper per kilowatt hour than using oil or electricity for heating. Another option is heat pumps, which use the compressor technology of the refrigerator to collect heat from the air, water or ground, magnify it and transfer it to water or air. The output can be up to 3, 4 or 5 kilowatts for every kilowatt of electricity used to run the pump. Obviously, the source of this electricity must also be considered. In Sweden, 95% of new homes have heat pumps fitted as standard. The UK has the greatest potential to use wind power in Europe and currently has an installed capacity of 20 megawatts. Large areas of Scotland have the resource available to generate over 1,800 watts per metre squared of power. Wind turbines work by converting kinetic energy into electrical energy. Often wind speeds of over 5 metres per second are needed for a reliable supply, and a turbine sited near obstacles or in an urban environment will generally have a lower output than one sited in an open environment. We also have massive potential to install hydroelectric schemes, tidal or wave power schemes. These hugely untapped resources have the potential to meet more than double the UK's electricity demand. But what can we do in our homes and offices? Solar radiation can be captured and used to produce electricity via photovoltaic panels or via solar thermal technology to heat water. This video will focus on using solar energy to meet our needs in this way. Sunlight's all around us. There's more energy available from the sun each year than is estimated to be available if we pooled our entire future supplies of coal, oil, uranium and gas. When compared with other renewable resources on a global scale, solar energy is by far the most plentiful and far exceeds our annual energy demand. The UK receives, on average, 800 kilowatt hours per metre squared of solar energy. Less, perhaps, than other parts of the world, but plenty for what we need. On Earth, we receive about half of the sun's energy once some has been absorbed and reflected. Some of that energy will be direct radiation and the rest will be diffuse radiation, which is passed through clouds or reflected from surfaces. We can use both of these types of radiation to produce energy. The solar energy we receive varies as the sun follows a different path dependent on the time of year and location. It will also be at different height depending on the time of the day. To maximise the potential gain from solar radiation, the angle of any solar collector and the direction it faces or its aspect are vitally important. Irradiance which falls at 90 degrees to the apparatus is most effective. In order to maximise the time when the sun will be at this angle, a simple rule of thumb is to set up any collector at 0.9 times the latitude of your site. This can significantly increase the energy produced by up to 20% in winter and 50% in summer.
The technology industry must balance the economic impact, environmental impact and energy output from any technology. So can that really be done? And how much energy can we get from the sun if we try?
At Napier University in Edinburgh, the hourly direct solar radiation and hourly global radiation on a horizontal surface were recorded for a year. As you'd expect, there's more energy available in summer than in winter. From this hour-by-hour data, by applying detailed calculations which account for solar geometry, it's possible to calculate the total radiation per square metre for any given angle of sloped surface facing in any direction. The technical calculations involved are beyond the scope of this video, but there are many books and articles available if you wish to tackle this calculation yourself. The calculations predicted an annual available solar energy of 1,037 kilowatt hours per metre squared if a collector is sited facing south at an angle of 40 degrees from the horizontal. So what does that actually mean? How much electricity or hot water can we get from that? Later we'll look in detail at a thorough assessment of the calculated energy output from photovoltaics and solar water heaters for this campus at Edinburgh Napier University. We'll also look at the financial costs of meeting the energy needs of the campus from solar energy. The first step, before we look in detail at the technology itself, is to work out how much space we have and how much of it can be used to give the best results. Photovoltaic systems work to less than half their maximum efficiency if they're sited in a shaded area or if they're not placed at the best angle for their location. It's therefore very important to maximise the use of space and minimise shading when you're choosing a site. It's not always necessary to install renewable technologies on your actual building. However, to reduce transmission losses, it's preferable to site them where energy demand is. At Napier University, there's several choices of available surfaces for installation of solar collectors. Areas which are regularly shaded are not considered for the purpose of this assessment. As we've said, this would reduce the panel's performance. The roof is the preferred site, as there will be no restriction on the angle or aspect of the panels. All walls have a restricted aspect, and it's likely that the front of the building will have the angles of the panels affected by planning permission. None of these issues are insurmountable, but they must all be considered. If the size of the panel and the angle are known, then the area of roof required per panel can be calculated. It's possible then to cover the entire roof with panels. However, it'll be more efficient to leave space between panels to prevent shading from low winter and evening sun. For a south-facing aspect, the sun's altitude varies over the year from between 18 degrees and 88 degrees, and this needs to be accounted for. Optimal spacing allows for half of the available roof space to be covered, giving a maximum area of 1,930 square metres available for photovoltaic and solar thermal collectors at Napier. The same calculation could then be carried out for the walls if further solar panels were required. Because of the lack of restrictions on angle and aspect when using the roof, it's possible that soon we might find ourselves fighting for available roof space and organisations profiting from renting out their roofs to others. Now that we know how much space we have and how much solar energy per metre squared of that space, we need to start looking at what level of demand we're aiming to meet and how to calculate the expected outputs from any technology that we use at this site.
In the past, the first thought when installing any renewable technology would have been how much energy do I need? But now, with the financial incentives that we've talked about, the question's moving rapidly closer to how much can I possibly manage to generate.